Okay, welcome everyone to the CHIME FRB Journal Club. We have a very exciting installment today. We have an external speaker who will be talking to us, Navin Sridhar, who will be telling us about FRBs from X-ray binaries. So Navin, please take it away and tell us all about your interesting paper.
Thank you, Emily. Thank you so much for inviting me to discuss our work with you all. I'm very keen to discuss about the various pros and cons of our work and its observational implications. So this is not a talk where I'll be convincing you all why X-ray binaries can produce FRBs, but this will be a talk where I will share our agnostic investigation on what conditions accreting X-ray binaries need to meet in order to produce FRB-like emissions. So that's the overall idea. And so this is the group that least needs an introduction about FRBs, but I'm still going to give a very brief introduction for any viewer online. So FRBs are mysterious radio signals of millisecond duration. So this duration sets a limit on the emitting size, the size of the emitting source in some sense. The luminosity can span anywhere between 10 to the 37 to 10 to the 46 erg per second. And given that they are in the radio band and they are so luminous, the brightness temperature of such bursts are extremely high, of the order of 10 to the 35, 10 to the 37 Kelvin, and therefore such bursts require coherent emission mechanism. And we know that most of the earlier discovered FRBs had very large dispersion measures of the order of a few hundreds of parsec per centimeter cube, which hinted that these signals are extragalactic in origin. And we know that FRBs can repeat, and some of them can even be periodic, with a period lasting between a few days to a few months. So here by periodicity, I don't really mean that we receive a single pulse of an FRB every period, but we see a burst of FRBs. We see an active cycle of FRBs happening every period. Yeah, so if the FRBs arrive for 10 days over a period of 100 days, then you have an active duty cycle of 10%. That's what I mean here. And certain FRBs can also show frequency dependent active phase window. So if the active phase window is 10 days, for example, then some FRBs have shown that the higher frequency bursts arrive during the earlier phase of the active window, and then arrives the low frequency burst. And also that the active phase window of the higher frequency bursts are relatively shorter than the low frequency bursts. So as you can see, the green curve corresponds to a high frequency ones, the red ones correspond to the low frequency one, and the entire band is the active phase window of an FRB called 180916. And so what you see here is a single FRB, and FRBs come as several packets together as packets of bursts. And within a single FRB, particularly for the repeating classes of the FRBs, what we see is that the high frequency packets of bursts arrive earlier than the low frequency ones, and this is observed after correcting for the dispersion measure and dispersion delays. So what is the current state now? So the best studied engines of FRBs are based on magnetars, because magnetars can host various mechanisms to produce FRBs, including shocks from their flares, curvature radiation, reconnection, free electron laser, and so on. So it's a very versatile source, and they can also explain to some extent the burst energetics, individual burst energetics, the repetition because flares repeat, polarization angle, and millisecond timescales, and so on. And also that the locations of FRBs are more or less consistent with core collapse supernovae, which are the birth sites of magnetars. And we also have a direct evidence from the FRB 2004-28 which is a galactic FRB, which was observed from a magnetar 1935 plus 2154. So this is a smoking gun evidence that magnetars can indeed produce FRBs, although it is not really clear whether all FRBs are produced by magnetars. Why? Because yeah, so I'll say why we need to look beyond canonical magnetars. By canonical magnetars, I mean the ones that are formed from a supernovae and the relatively slow spinning ones. So if you look at very actively repeating sources like FRB 121102, we don't really have magnetars in our galaxy that are active enough to produce the bursts that are seen from 121102. And speaking of periodicity, there are some models of magnetars that invoke precision to explain the periodicity, and these processing models predict a second shorter periodicity from the neutron star rotation itself that should be detectable in the FRB pulse train. And no such intra-window periodicity is observed, which sort of disqualifies many precision-based magnetar models. Furthermore, the limits on local scattering, absorption, and DM dispersion measure variation suggests that, at least from 1809, FRB 1809-16, that the FRB pulses are not really surrounded by any dense supernova remnant, which is expected for a young precessing magnetar. So speak of energy budget. So for example, a magnetar with a 10 to the 50 erg of energy in its magnetosphere can produce, say, at most around 10,000 FRBs with a luminosity function similar to 121102 at an efficiency of 10 to the minus 4, 10 to the minus 5. So 121102's rate is, say, around 5 to 6 bursts per day on an average. It should have produced around 15 to 20,000 bursts in the last decade since its discovery. So going by this, it should stop very soon, or at least start showing some secular changes to its luminosity function if the energy for producing 121102 is actually coming from the 10 to the 50 erg of a magnetar's magnetosphere. However, there doesn't seem to be any such secular changes to the luminosity function of 121102, at least to our knowledge. So locations, while the locations of magnetars and FRBs are consistent with the hosts of the galaxies themselves, it's sort of inconsistent within the host galaxies. So I'll talk about this very soon. And so these are some of the sticking points with magnetar-based FRB models that makes us think whether multiple progenitors can exist for FRBs. So the inconsistency with the offsets within the host galaxies is recently shown in a work by Sridhar. So this is the Hubble observations of FRB 1809-16. This is the host galaxy, and what you see here is the green dot that you see here is the location of the FRB, and the dark patch here is the nearest star-forming region. The distance between the nearest star-forming region and this FRB was found to be around 200 to 250 parsec. This is a very crucial detail. Why? Because during the birth, magnetars, the neutron stars, are shot with velocities of a few hundred kilometers per second due to their natal supernova kicks. Going by this, a magnetar or a neutron star would need a few million years to traverse the distance of a few hundred parsec, which the FRB 1809-16 is from its presumed birth site, that is the nearest star-forming region. This is problematic for models that require young magnetars with ages of around 10 to 100 years, since such sources are invariably found close to their birth sites. So this time scale of a few million years that's taken to attain an offset of a few hundred parsec is, however, consistent with typical X-ray binaries, with high mass X-ray binaries with, say, a 10 to 20 solar mass post-main sequence companion star undergoing a mass transfer. So these advancements from recent observations mostly accelerated by CHIME, and some more sticking points of magnetars that I mentioned earlier motivate us to understand accreting X-ray binaries better and to investigate them agnostically to see what conditions they need to meet if they were to produce FRBs, and start evaluating the prospects of accreting compact objects to power FRBs a bit more seriously. So X-ray binaries. So from here on, I will try to motivate you why X-ray binaries can be good candidates, and what are the conditions they need to meet in order to emit something like an FRB, and if they can meet such conditions. So there can be different uh, uh, types of X-ray binaries. They can be transient or they can be persistent accretors, and they undergo something called state changes during their outbursts, and such state changes can give rise to radio jets. So what you see here in the right hand side panel is how the X-ray hardness changes during an outburst. So the outburst starts here, where you observe very hard X-rays from an X-ray binary, and then the luminosity increases, and then slowly you start seeing soft X-rays during the peak of an outburst, and then the luminosity decreases, the hardness increases, the hardness of the X-ray increases. So during this hysteresis loop that some X-ray binaries traverse during their outburst, different types of jets are also seen. Yeah, so these jets that are seen from galactic X-ray binaries and such sources that emit these jets are called microquasars. One is steady jets that are seen during the hard states, typically during the onset of an outburst. So the light blue colored jets with small Lorentz factors, these corresponds to the steady jets. And the other type of jets that we know of are the transient flaring jets that are usually seen during the bright, hard to soft intermediate state transitions. These transient flaring jets are faster. They have much larger Lorentz factors. And we have some evidence of such flaring jets from galactic microquasar, for example, SS433. What you see here is a 40-day GIF of VLBI image of SS433. You can see these transient flaring jets that are emitted, and also that the jet is persistent. So initially, you see that the blobs are emitted along this direction, and slowly it starts emitting at some other direction. So these jets do persist. And as you can see, these blobs can get brighter as they traverse far away from the source, and these could be because of internal shocks. And jets are powered by the magnetic field that is pinning down onto the black hole and the accretion disk, and the magnetized internal shocks can give rise to something called synchrotron maser. And such synchrotron maser this is the mechanism that we are invoking to the most promising mechanism, at least in this scenario, if you want X-ray binaries or accreting sources to emit FRB-like sources. So I'll quickly go through what synchrotron maser emission mechanism is. So you have a shock that is moving into the upstream medium, and you have a downstream medium here. You have an magnetized. So these are perpendicular magnetized shocks, by which I mean the magnetic field lines are perpendicular to the normal of the shock plane. What happens is that the upstream particles that are that enter the shock, they gyrate around the magnetic field lines, and the important point is they gyrate coherently in the shock field, and the shock particles from an unstable, they form an unstable ring-like structure in the momentum space. So here I plot, it's not my plot, here I show the simulation from Hoshino and Ahrens, where you see that in the momentum space, the particles form a ring-like structure because of these gyrations. And this is similar to a population inversion that you observe in many lasers. And such population inversion corresponds to metastable state. And this is continuously replenished by upstream particles that enter the shock. And then, since this is not a very stable structure, it collapses coherently, and such coherent collapse gives rise to electromagnetic waves. And such electromagnetic signals are actually observed from first principle kinetic particle in cell simulations. Here you see BZ, EY components, which correspond to electromagnetic waves because of these synchrotron maser emission. And this can be very similar to what FRBs are. So that is the emission mechanism. And now I'll get into the overall engine, how the engine operates that we are envisioning here. So before I get onto the engine, any questions up until this point?
All sounds good.
Okay, so I'll talk about the engine now. So you need a black hole of mass m with a spin a, and what you have is a companion star that undergoes a thermal or dynamical timescale mass transfer into a black hole at a rate that exceeds the Eddington rate. I'll tell why we need a transfer rate that exceeds an Eddington rate very soon. The super Eddington accretion flow is radiatively inefficient, which leads to puffing up of the inner disk. This leads to powerful outflows in the form of accretion disk winds, and these winds can therefore reduce the accretion rate closer to the black hole compared to what the original star actually gave off. So m dot here is less than m dot here. These mass-loaded disk winds also play a very important role in shaping the polar accretion funnel, and this helps in collimating the jets that are produced finally. The jets during their transient, the ballistic or transient jets that I talked about earlier, they carry flares. These flares can be produced at the base due to reconnection events. I can talk about it later if you have time. And they are ejected from near the ISCO. These flares propagate outwards along the jet funnel, and at some radius, it develops a magnetized shock into the cavity of a previous quiescent jet. So if you remember, the steady jet here is the medium onto which the transient jet is going and ramming into. That's the picture. So this leads to powerful shocks at some radius, at some deceleration radius. So such magnetized shocks can harbor synchrotron maser instability, and this can give rise to an FRB-like emission along the jet axis. So note that the shock forms and eventually radiates at a radius of several astronomical units, at which point, so this is much farther away from the innermost regions of the black hole, where the wind is stronger. At these radius, the environment is quite tenuous, and the effects of induced Compton scattering is negligible. The jet is aligned with the angular momentum axis of the inner accretion disk, and if the spin axis of the black hole is misaligned with respect to the angular momentum of the inner accretion disk, then the direction along which the jet is oriented will change due to the length-steering precession of the inner disk, and therefore the direction along which the FRB is emitted will also precess across the spin axis of the black hole. And we think, so in this model at least, this precessing behavior of the FRB emitting jet can cause the periodicity that is observed in repeaters when the jet axis passes through the observer's line of sight. So this comes with a duty cycle, which goes as the which is directly proportional to the width of the jet, the opening of the angle of the jet, and it is inversely proportional to how inclined the jet is away from the spin axis. So that's the overall engine. So with this, we look into the luminosity of the FRBs that will be produced through this channel. So what you see here is the observed luminosities in the y-axis and the duration of the burst in x-axis of repeating and non-repeating FRBs as filled and non-filled gray circles.
May I ask a question?
Yeah.
I'm sorry, just can you go back to your previous slide? I'm just thinking about the precession. So the precession, you said it's a lens Turing precession. So in other words, that's something that I guess doesn't damp. That is, it's a GR effect. And so that just will precess forever. Is that how that works?
Yeah. So the periodicity does not change because of the precision here. Yeah.
So I guess what can influence, so I'm just trying to remember, lens Turing precession. It's a purely relativistic dynamical effect. So it doesn't matter what's in the disk. So in other words, the m dot and, if that changes or there's fluctuations in that should not change that 16 days. That's basically what you're saying. Is that right?
So the m dot largely influences the geometric opening angle of the jet. So if you have a larger m dot, as a result of which, what you would expect is that the beaming fraction of the jet will change. So m dot will change the duty cycle because the beaming fraction becomes smaller. So if you, for example, if the m dot is larger, then the jet will be emitted to a much sharper beaming angle, and this will give rise to a much smaller duty cycle. And that's how m dot influences, in some sense, the periodicity in the form of duty cycle.
And so then whatever emission you have coming from that jet's going to have to be somehow geometrically separated into frequencies. In other words, the fact that the active time is different at the low-FAR band than at the CHIME band is going to have to be built into this somehow. Okay.
Absolutely. Yeah, I'll come to that.
Okay.
Yeah, exactly. Mohit, do you have a question?
Oh, yes. Actually, Navin, I'm just wondering, because I know in the millisecond magnetar model, we say that the outside environment, the circumburst medium should be clean. So do you have the same constraint in this model as well?
Yep. I will. So, okay. Okay, so there is an extensive analysis that we do in our paper to show or to see what kind of environment the central engine must have in order for the dispersion measure to be within 1 or 2 parsec per centimeter cube, because that's what is seen from the 1809-16's recent paper by Pastor Marazuela, I guess. So, okay, yeah. For a given m dot, say if the m dot is say 10 to the 4 in Eddington scaled, then what you would require is that the quiescent jet power and the quiescent jet Lorentz factor to be to the left side of this band, because this is constrained by the observed dispersion measure. So the upstream medium and the environment is definitely taken into account, and accordingly the jet property should also vary in order to produce an FRB that matches the observations.
Okay, thank you very much. I was just wondering whether this constraint would actually give us a lower limit between the waiting time, like of the bursts that we repeat bursts that we detect from a given FRB.
I have to think about that, because the waiting time, which is equivalent to the duty cycle in some sense, here it mostly depends upon the mass separation rate and the opening angle of the jet. But I have to think about whether how the environment will affect that. Yeah.
Okay, thank you.
Yeah, no problem. Okay, so as you can see, most of the FRBs, especially the non-repeating ones, are brighter than the repeating ones, and they require super Eddington rates in order to be explained. And I was talking about the top x-axis. The top x-axis shows the characteristic minimum time scale for energy released from a black hole engine, which is set by the light crossing time of the innermost stable circular orbit. So, and the colored contours depict the Eddington scale mass transfer rate that is required to produce a given accretion luminosity. So, for example, to explain, say, FRB 8916, one needs to have an accretion luminosity of 10 to the 40 ergs, and that can be produced by some 100 solar mass or 150 solar mass black hole. For example, it has a wide error bar, and the mass transfer rate should be around 10 to 100 Eddington scale mass m dot. So that's what this figure says. So when you place the observed FRBs in this map, we see that the non-repeaters preferably occupy a high luminosity, and this is reasonable because we can expect the non-repeating bursts if the period is very long, or the duty cycle is short, and the short duty cycle can be expected for smaller beaming fractions. Again, smaller beaming fractions can be expected at larger accretion rates. So this is understandable in this setup, in this model. The vast majority of accreting galactic neutron star black hole sources residing in long-lived X-ray binary systems with mass transfer rates at or below the Eddington rates, which, however, cannot explain most of these bright bursts that I have put in this plot. We need super Eddington rates. And stable thermal timescale mass transfer is, in fact, capable of generating sustained levels of super Eddington accretion. This can occur when an evolved massive companion star undergoes a Roche lobe overflow when it is on its way to become a giant. However, for thermal super Eddington accretion, the disk winds carry a lot of matter away. Like I said before, the star sends a lot of material, but due to the disk winds, only a fraction of it reaches the black hole, and this is not helpful. So if we also account for the disk winds, we show that the maximum attainable mass transfer due to a stable mass transfer is given by these dotted lines, which is around 10 to the 41-ish ergs per second. And that is, again, not enough to explain most of the FRBs. So, so we need an unstable mass transfer in order to explain most of the bright FRBs. And these unstable mass transfer can happen, for example, if and when a companion's star's stellar envelope becomes fully convective when it's approaching the Hayashi track, and the adiabatic response of the star to mass loss would be to shrink its Roche lobe. This leads to dynamically unstable mass transfer. And these unstable mass transfer phases can give rise to extremely large luminosity accretion for a very short period of time. Not very short period of time. The period of it can be a few centuries as well.
Centuries. You said centuries. Oh, 10. Oh.
10 to the 5 maximum, yeah. Decades to few decades to centuries.
Oh no, I thought you were going to. Yeah, I misunderstood. I thought you were going to talk about the timescale of FRBs, but you're talking about a lengthy period during which okay, sorry, go ahead.
Yeah, exactly. These unstable mass transfer phase can last for a long time also. So yeah, and the aftermath of such unstable mass transfer phase is a common envelope phase where you have a black hole or a neutron star, and it is surrounded by a common envelope from the companion star, and this will give rise to a more polluted environment, and therefore FRBs will cease to exist, cease to be emitted from the source after some time, and this can be seen along with luminous red novae. So yeah, many such stringent constraints need to be met by accreting X-ray binaries if they were to produce FRBs. Some good candidates are ultraluminous X-ray sources. So if FRBs arise from mass transferring binaries similar to ULXs, then they might be expected to occupy a similar host galaxy and location within their hosts. The hosts of FRBs and ULXs are generally forming stars at lower rates than the normal galaxies at a given stellar mass. For example, below the main sequence star formation, the dark black region here, they are all below it, with a locus of the star forming rate of around 0.1 solar mass per year. So it's consistent, it's good. And the mass, however, so the mass histogram is over here for the green ULX host and the orange FRB host. However, comparing the FRB host galaxies at gigaparsec scales to nearby galactic populations such as ULXs at few tenths of megaparsec can be a little problematic due to the cosmological evolution effects, particularly the shift in star formation to lower mass with decreasing redshift. On the other hand, ULX surveys are also systematically biased against low mass galaxies due to various selection effects. So we cannot really comment on this very conclusively right now. If you look at the metallicities, FRB and ULX hosts seem to sort of prefer lowerish metallicity hosts. However, FRB hosts do not definitely exhibit as strong a preference to low metallicities as, say, long duration GRBs or superluminous supernovae. But yeah, the prevalence of ULXs at similarly relatively low metallicities is also understandable given the prevalence of more massive black holes at lower metallicities. So if you look at the offsets, the peak of the FRB's offset and that of ULXs do match very well, and the FRB, and we do not really have a lot of samples for FRB offsets right now as much as we have for ULXs. There's a spike at large FRB offset, which is not seen in the ULXs. That's because our ULX sample is again biased against larger offsets. The ULX sample that we draw is only from within the D25 region of the host galaxy, that is the radius of the isoport where the observed band surface brightness is 25 mags per arc second square. So the spatial distribution of the ULXs within their host and are limited by the radius of the selection region and is devoid of sources with larger offsets. So that's okay. So with these similarities, we look further into other aspects of ULXs and develop this this model on that to explain other features of FRBs. So if you look at ULXs, there are, or any other accreting X-ray source, there are two periods in the system. One is the orbital period, and the other one is the length steering precision of the inner disk. And we know that the jet follows the length steering precision of the inner disk, which can last for a few days, from a few days to out of 1,000 years. So what we do is we establish a relationship between the orbital period and the length steering precision period, which is shown here for different properties of the system for different spin. So this is the fiducial case. The black lines correspond to the fiducial case of a 10 solar mass star with a black hole with a spin of 0.9 and secondary to black hole mass ratio of 1. And we look at what the precision period should be for a given orbital period for different systems parameters. The thickness of the bands indicate the allowed range of precision period for a given orbital period. And this range is obtained from the uncertainty or our lack of understanding of the accretion disk winds or the mass transfer rate. How much mass is lost in the winds. So that is encapsulated in this error range in some sense. So in this plot, what we have plotted is different ULXs. So we have orbital periods of some ULXs, and ULXs also show some superorbital modulations. And we interpret the superorbital modulations of certain ULXs to correspond to the inner disk precision. And when we plot it here, we see that the ULXs can actually very well represent the currently known periodicities of these two FRBs with a given orbital period of the system. Another independently, we also show that ULXs are likely to be extreme mass ratio binaries or equivalently intermediate mass X-ray binaries, because these ULXs from observations, they actually fall in this pink band corresponding to intermediate mass black holes. So coming to the chromatic properties, so we all know what this figure means. The high frequency bursts arrive earlier and then arrives the low frequency burst. The active phase window of high frequency bursts is shorter compared to the low frequency ones. That's observed from 1899 and 16 by Pastor Maraswela. I'll now use this cartoon to explain how this very crucial observational evidence can be explained by operating jetted binaries. The FRB emitting flare. So in this cartoon, I have aligned the jet along with the black hole spin axis, and that is not necessarily always the case. This is just for an example. Okay, so the FRB emitting flare, ejecta, is launched ballistically outwards along the jet axis, along the axis of the jet. In the synchrotron maser scenario, the peak frequency of the radio emission scales with the properties of the FRB generating transient flare, LF, and the pre-existing quiescent jet, the pre-existing media onto which the flare goes and hits. That is LQ, luminosity of the quiescent jet, magnetization of quiescent jet, and the Lorentz factor of the quiescent jet, gamma Q. MHD simulations of relativistic magnetized jets by Sasha Chkowskoy in 2008, I guess. They show that the jet pointing flux is concentrated in a hollow cone around the jet core. That I've shown here. So the jet is structured about its own axis. The jet is not uniform around its axis, but the properties of the jet change across the jet axis. That is along the theta direction here. Therefore, the FRB emission, so I'll explain this plot here. The gamma Q is the quiescent, the Lorentz factor of the upstream quiescent jet. It is very small at the spine or the spine of the jet, and it is larger somewhere away from the spine of the jet. Eta Q is the power of the jet, and the power of the jet is again larger at the sheath of the jet compared to the spine. So the jet is structured, and we see this from MHD simulations, and it is a natural consequence of the fact that the magnetic field lines are the anchoring the accretion disk and the black hole that is giving rise to these jets are not uniform. So therefore, the FRB emission coming from the jet will also be different depending on where they are coming from. For example, the FRB emission coming from the edges of the jet with a higher gamma Q. So gamma Q is a solid line, is larger near the away from the spine of the jet. So we'll have a larger gamma Q, and larger gamma Q corresponds to a lower frequency. So the emission that is coming away from the spine of the jet will correspond to a lower frequency and will peak at lower frequency. And the FRB that is coming from the spine of the jet will correspond to, will peak at a higher frequency. The emission comes out at a radius larger than the shock deceleration radius, or DEC, and this shock deceleration radius depends upon the upstream Lorentz factor. It goes as 2 gamma square CTF, and it depends upon the upstream Lorentz factor. Due to the structural nature, this radius is shorter for flares interacting with the spine of the jet compared to the interaction produced near the away from the spine, because near the spine, the Lorentz factor is small. So if the Lorentz factor is small, the deceleration radius is small. So the emission radius is also smaller. So the high frequency bursts that are produced from the spine are produced much closer to the black hole. And after a while, the flare passes a larger radius, and then the low frequency bursts are produced. So a part of this is already explained now, which is the fact that the high frequency bursts during an active phase window arrive earlier than the low frequency bursts. Okay, good. Furthermore, the width or the duration of the burst is also proportional to the emission radius. So according to this model, we also predict that the low frequency bursts that are produced at a much larger radius should be broader or should be wider in the FRB duration should be wider compared to the high frequency bursts that are produced closer at a smaller radius.
Oh.
If you assume a spherical expansion, which is reasonable. And yeah, so it determines the emission frequency, determines the arrival time of the burst, determines the burst width. So one thing that is not yet explained is the active phase window of different frequency of bursts. I'll come to that very soon. So observations suggest a curved quiescent jet cavity. The jet cavity that I've drawn here seems to be tilting towards the earlier orientation, the gray cone that I've shown here, due to the drag of the precessing disk winds. This curvature that we are envisioning is not really just imaginary. This is an actual VLB image of the corkscrew pattern of the inner disk winds and the quiescent jet. And you can clearly see the curvature of the jet that I was talking about earlier.
What's the scale here?
This is, okay, I forgot the scales here. This is several astronomical units to parsec scales, I guess. Yeah, this is large scale. I don't exactly remember it now. But I can say something regarding the scales. The deceleration radius that we require here is of the order of astronomical units, RD. So yeah, the bursts are produced at much larger distances of astronomical units.
Okay.
So yeah, the curvature of the jet that I've shown is not really imaginary, and we have seen that, and the FRB passing through this corkscrew pattern can perhaps give rise to some variations in the DM, RM, and so on. Coming back to this, so if the outflow is directed across a narrow range of angles, that is along the core of the jet, that is again for high frequency ones, this could potentially result in a shorter phase window for them, because compare and a larger phase window for the burst coming from the sheath, because the interaction time for the flare along the sheath is longer compared to the interaction time of the flare with the spine of the jet. Therefore, the active window for the low frequency bursts that are produced away from the spine of the jet is also expected to be a little bit longer compared to the high frequency ones that are produced from the spine. Yeah. Any questions about this before I jump on to the next one? Yeah, Vicky.
Yeah, so earlier you said that here you were assuming that the black hole spin was aligned with the jet spine, I guess is what you said. Which you said you could relax that assumption. I guess what I'm really wondering is the frequency ordering of the active phase window going to be universal in all such systems that we ever discover? Or depending on the angle that you see it, you might see different ordering of those active phase windows as a function of frequency.
So answering your first question about the alignment of the jet with the spin, that is just for illustrative purpose here. and that need not necessarily be the case. The jet can, and the jet does align away from. So you should imagine this like, so you have the spin axis here, and the jet is behind the spin axis in some sense. That's how you should imagine this figure, or ahead of the spin axis in some sense. That's how you should imagine this figure. So the jet is not aligned with the spin axis, but it is behind or in front of the spin axis. So the second, your second question was about this
How universal should
hierarchy.
the frequency ordering be?
Um,
Like, will it always be the case that the one frequency comes before the other in this model?
so it depends upon the structuring of the jet here. And the structuring of the jet, by which I mean the Lorentz factor, how it changes within the jet axis and how the power changes within the jet axis. These parameters depend on various other factors, including the spin of the black hole, including how far, including the level of magnetically arrested accretion disk it is, what kind of field geometry it is, and so on and so forth. So this expectation of high frequency bursts arriving earlier compared to the low frequency ones can work for such structured jets, but it need not necessarily work always if the underlying conditions are way different. For example, if the upstream medium, if the contrast between the upstream medium and the flare is not large enough, that is, if the luminosity of the flare is not large enough compared to the upstream medium, then you would not expect such you would not expect these chromatic properties. So yeah, so in short, these chromatic properties can be produced by such structured jets, but not all jets need to produce such chromatic properties.
Okay, thank you.
Yeah.
Navin, I'm just mindful of the time. Maybe about 10 more minutes.
Sure. Thank you. Okay, I'll jump to some predictions from this picture. Multi-wavelength counterparts. The mass loss rate in super Eddington winds is expected to be, yeah. So first you have the persistent. You can expect persistent counterparts to the source due to the shock ionized parsec scale optical X-ray radio bubbles, and these bubbles are inflated by the jets to a few parsec scales, even to several hundreds of parsecs. Such luminous ULX outflows are, and these are observationally known. You can also have compact synchrotron radio source co-located to. So the compact synchrotron radio source that is co-located to FRB 121102 at around 1 parsec, I guess, could also arise from young ULX bubble from a binary star undergoing unstable mass transfer. So yeah, 121102 is consistent with this picture. And then you can have post-FRB transient that can be a luminous red novae that can happen after a common envelope phase. And then you can also expect some high energy neutrinos. Although most of the stellar mergers in Milky Way and nearby galaxies are due to two stars merging, a merger between star and a black hole is also possible and can give rise to luminous red novae. And such events will be accompanied by turning off of FRBs. And the luminosity of such luminous red novae can be anywhere between 10 to the 39 to 10 to the 41 erg per second. So it's not extremely bright, and it can be detected by future facilities like Vera Rubin Observatory if the if the unstable mass transfer occurring system is at a few parsec or few megaparsec or tens of megaparsec. And then contemporaneously, you can also expect incoherent thermal synchrotron emission due to the shock itself. It can range from optical to gamma rays, and it depends on what the upstream composition is, whether it is leptonic, whether it's electrons, positrons, or whether it is baryon loaded. If it is baryon loaded, you expect an optical, and if it's paired plasma, you can expect X-ray, gamma ray as incoherent thermal synchrotron due to shocks. And another prediction is narrow active window for bright bursts. Like I said before, for a bright burst, you need a larger accretion rate, and larger accretion rate will give rise to a much narrower or much higher luminous jets, or much narrower jets equivalently, and such narrower jets will lead to less chance of detecting bursts from them, because the duty cycle would be smaller. So lower probability of detecting repetitions from brighter bursts. By brighter, I mean the bursts with larger isotropic equivalent luminosity. So this is again consistent with our current observations, because the non-repeaters are the ones that are occupying the higher luminosity end of this diagram. And that's one of the expectations of this model. And the burst duration is shorter for high frequency bursts and longer for low frequency bursts, because of the radius effect that I talked about earlier. And another prediction is systematic variations to the burst properties of very bright FRBs. The ones that are coming from unstable mass transfer phase will go through common envelope, and so the immediate environment will be very polluted. So the dispersion measure, for example, can increase. That can be observed, and due to much larger sudden increase in accretion rate, the luminosity of the bursts that are seen will also increase, and eventually they will turn off. Slow radio bursts. This is an exciting possibility, because the duration of the bursts, they scale with the mass of the black hole, because the characteristic minimum time scale for energy released from a black hole engine is set by the light crossing time of the ISCO, which is dependent upon the mass of the black hole. So one can also perhaps expect slow radio bursts from intermediate mass black holes, or even perhaps AGNs at a few seconds duration, just that we have to be sensitive enough to observe them. Okay, I think I will leave here and take any questions if there are.
Awesome. Thank you so much, Navin. That was a really, really interesting talk. Do we have any questions? Had several already, but feel free to jump in or raise your hand.
Yeah, Mohit.
Mohit?
Sure. Thank you very much, Navin. It's a very interesting talk. So you showed one plot where you actually plotted on the x-axis the mass of accreting source, and on y-axis its luminosity. I think this is the second plot that you showed.
Mm-hmm.
Can you go to that? Yeah. You can guess, like, I'm interested in this point, the star that you plotted for repeater. Now, looking at this plot, I see that you require very low accretion rate. So means the fraction of super Eddington, it should be like, it's not super Eddington, so it's more like low mass X-ray binary, or maybe high mass X-ray binary, the mass transfer rate. And it is, but you said that I'm not really sure whether the argument is based on purely on energetic, or maybe there is some important sort of aspects of synchrotron maser emission model that is based on the requirement of super Eddington rate. So I'm wondering whether this low accretion rate is permissible in this model.
Yeah. So quick answer is yes. Just that, like you said, you don't really require ULXs for that. You just require low mass X-ray binaries, and they should be enough. And for a luminosity of around 10 to the minus 37, sorry, 37 erg per second at 3.5, 3.6 megaparsec, which I think is the distance of M81. The flux, X-ray flux that you would see from an accreting source would be 10 to the minus 13, 10 to the minus 14 erg per second per centimeter square. And that is barely detectable by, say, Chandra if you integrate for several hundred kiloseconds, several hundred seconds, or several hundred kiloseconds, I mean. It is also, so this is purely from the energetics that I talked about earlier. If you want to relate it to the synchrotron maser emission mechanism, this is somehow related because the efficiency of the maser is assumed to be 10 to the minus 3 here, by which I mean, so the total energy that is hitting the shock, what fraction of it is getting converted into an FRB, that is assumed to be 10 to the minus 3 here. If that is different, you would expect this point to also change vertically. But this 10 to the minus 3 argument is well motivated by kinetic first principle particle density simulations.
Okay, so I have a follow-up question. Can I ask, Emily? It's a very short.
Sure.
It's a quick one. So in that case, I feel that your model can be applicable to even galactic low mass X-ray binaries or high mass X-ray binaries. You don't actually really need an exotic system.
Yeah.
So why haven't you seen any FRB or why high emission burst from galactic sources?
Yeah, because we don't. Okay, we know of around a few dozens of galactic black hole X-ray binaries or low mass X-ray binaries. It can even be a neutron star. And the requirement for this to work is that the jet has to pass through your line of sight. And out of these galactic black hole X-ray binaries, only a small fraction of them are microquasars, that is, the ones that are known to emit jets. And a very handful, just a few of them are microquasars. And none of them actually have their jet oriented along our line of sight.
Okay, so you are saying just by chance, but I add that we are more than 400 X-ray, low mass X-ray and high mass X-ray binaries discovered to date. But yeah,
more than 400 what?
Both, if we include both low mass X-ray binaries and high mass X-ray binaries, like cataloged sources, there are like more than 400. But yeah, I got you.
Sure, but you need a microquasar, which is a jet emitting X-ray binary, and only a fraction of them do that. And we do not really know of any jet that is persisting along our line of sight.
Is there any constraint on like what on the magnetic field or the accretion rate when you can form jets in these compact systems?
Yeah, so it depends on various factors. It depends on the spin of the black hole, because the jet is coming from, say, if it's from Blanford-Zach process, it is extracting the spin energy. So it needs to have it depends upon the spin of the black hole. It depends upon how much magnetic fluxes are directed, and there are and how far or close the inner disk is from the black hole during a particular phase of an outburst. So yeah, it depends upon various factors. So it's understandable that only some of them are jet emitting X-ray binaries, and not everyone does.
Thank you, Navin.
Yeah, no problem. So yeah, so
sorry, go ahead, Navin. Final thought.
yeah. So the promising candidates, I would say, are the jet emitting ULXs that we know of, because if you just go to larger distances, you can sample more and more accreting X-ray sources and of much larger luminosity, and these are more promising candidates to monitor using our radio dishes.
Nice.
than galactic sources. Yeah.
Yeah, no, that's really super interesting stuff. Okay, thanks. We probably have to wrap up now, so I will